My name is Phil and today I will be presenting problem 3 wing fountain. The problem reads, when a flat metal wing falls from a certain height to a water tank, it generates a fountain that can shoot water high into the air. Our task is, how does the maximum height of the fountain depend on the wing's parameters? In this presentation, I will first show my experimental setup and then go over the qualitative explanation. So, for the setup, we use two setups. The first setup is optimized for low release heights. The wing is held back at its sides by this Irish-shaped form and then falls through the hole, inducing the jet. Moving on, we then use a calibration with a checkerboard pattern. To obtain a high-speed video, we use a 1800 fps camera placed in front of an LED array, and for a full 3D tracking, place a mirror to get a perpendicular perspective with a second LED array. To extract then the height from this, we project the jet onto a wall and can film the shadow using a 50 fps camera. This is what all of this looks like in real life. And they were all placed far enough away to reduce parallax errors. With this, we have full 3-dimensional tracking possible. However, there's an issue. Taking a look at this example video, we can see here that we have a tilt of the wing during falling, which might be fine for qualitative observations, but later when we quantify all of this, it will impose a problem. For this reason, we use a secondary setup, which is optimized for great release heights and also uses an improved dropping mechanism. Taking a look at this dropping mechanism, we can observe that we use two magnetic actions along with a 3D printed bracket to hold the wing. To show you that this is an improvement, we can take a look at the dropping of the wing and see here that it falls almost perfectly straight with there being no tilt during the fall. As for the wing itself, it is made out of 3 different parts. 2 being 3D printed parts for the outer diameter variation and also the inner diameter variation, as well as a copper ring in the middle. The copper ring is there to ensure that the ring still has metal properties. With this we can state that the parameters of the ring are its inner diameter, its outer diameter, the thickness and its ring radius, which we can all vary independently. So, now for the qualitative explanation, which is very important for this problem. First, in a free fall, the wing is accelerated down due to gravity. As soon as it reaches the water surface, a cylinder of high pressure. So, the wing falls and is accelerated due to gravity. As soon as it then reaches the water surface, a cylinder of high pressure is reduced below the wing. And the cylinder of high pressure then pushes the water both inwards as well as outwards. Taking a look at it from a top view, we can observe, and then let's take a look at the inwards traveling water. The radial components then cancel out in a single point, and an upward jet is induced. Taking a look at the video, we can indeed see this upward jet. However, there's more. The outwards pushed water also creates a corona, as well as an air cavity forms in the former place where the wing used to be. Focusing on the further evolution of this air cavity, we can observe the water then starting to flow inwards again. This might remind one of a so-called vertical jet. Such a jet is produced when the cavity collapses and the momentum of the inwards traveling fluid is transformed in both an upward and a downward jet. A similar mechanism is acting here. However, this cavity collapses in not a single point, but rather a cylinder. For this reason, the second jet takes an irregular cylindrical-like shape. To further take a look at the phenomenon happening here, we can introduce a new type of plot. In this plot, in order to generate it, we squeeze each frame of the video to a single column and plot it over the time. In other words, the y-axis of this video relates to the y-axis of this plot, and all of the marked regions are regions where there's either water in the air present or air present in the water. So, now let's take a look at what's actually happening here. Taking a look at this plot, we can see every relevant phenomenon happening. In the beginning, we have the free fall of the wing until the water surface. As soon as it then reaches the water surface, a high jet is induced, which then breaks into the droplet. The wing also generates a corona, which then opens up the air cavity. When the cavity collapses, the second jet is then induced, and bubbles rise to the top. So, having covered the qualitative explanation of what's actually happening here, let's take a look at a quick relationship. And that is between the velocity of the jet and its height. The task asks us to take a look at the maximum height of the jet. And plotting the highest droplet of the jet, we can observe a simple parabolic relationship. Going one step further, in plotting its velocity against its height, and plotting in a simple ballistic relationship, we can once again observe that it fits perfectly. With this, I just want to state that between its velocity and its height, there's a simple ballistic relationship. So, now we move on to something more interesting, the qualitative parameter study. First, focusing on the initial, on the jet velocity on the wing radius, we can observe, when taking a look at the first jet, that on the right side here, there's almost no first jet at all. While on the left side, it's a very high-speed jet which quickly breaks into droplets due to being very thin. With this, we can state that the jet velocity decreases with increasing radius. Moving on to varying the impact velocity. This time, the timing of each video was adjusted so the impact velocities appear to be equal. In the first video, we can once again see that with this adjusted impact velocity, all three jets appear to be equally fast. It follows from this that the jet velocity is directly proportional to the wing velocity, which makes sense due to energy conservation. However, we also observe qualitatively different behavior in the second jet. Here we once again use wings with different inner radii. Then look at the second jet. On the left, the jet is so thin that once again breaks into droplets. It follows that the cavity then again collapses in a single point instead of a cylinder. And with this, we have a more natural and usual Worthington jet, while on the right side we are once again able to observe the Worthington cylinder. So, as we also want to quantify what's happening here, we can take a look at a theoretical model. For this, we can just imagine that in a certain time step dt, the wing pushes a certain amount of volume out of its frame. As the wing sinks below water, as water is incompressible, this flow has to go somewhere. So either contribute to the jet or contribute to the corona. We can define the fraction lambda to be the volumetric flow rate of this displaced water flowing into the wing. To actually now find the velocity of the jet, we can take a look at the kinetic energy transferred from the wing to the water in the time step dt. Writing out the expression, it is first important to mention that here we assume the wing velocity to be constant due to considering a small enough time step that the wing is not slowed down from the water. Going one step further, we can also state that the change in volume over time is simply just the volumetric flow we've defined from before. So, to further simplify this, we can take a look at the second term here and state that it's the acceleration term. However, it's important to mention that due to being incompressible, there's almost no energy in the acceleration, as it happens almost instantaneously. This we can drop this term and state that all of the energy is actually in the velocity and the volume of both the jet and corona. However, due to the low velocity of the corona and its low volume, we can approximate through experimental results that only about 4% of the actual energy is stored in the corona. With this, we can approximate the drop this term, further simplifying our equation, and now solve for the jet velocity, leaving us with this simple relationship here. However, as we currently have no way to find lambda, we can model a problem as a mixed boundary problem, stating that what is irrotational and incompressible, then stating that define irregular boundary conditions below the wing, stating that here the potential moves with the velocity of the wing, and on a free surface are Newman boundary conditions, stating that here the potential is equal, assuming atmospheric pressure. This can then be solved on a grid. And now moving on, and now taking a look at our potential correlates resulting from this, we can see that from the water flowing inwards, we can determine our factor lambda. Now comparing this to our theoretical results, we can see that plotting the jet velocity over the inner radius, it fits well. And with an increase in jet velocity, with an increase in inner radius. Going one step further, and plotting jet velocity over the outer radius, we can see a different thing happening. Here, the jet velocity increases as a greater pressure column induced below the jet, pushing more water inwards and giving more kinetic energy to the inner jet. As for jet velocity against the wing velocity, here we're able to observe the same trend, which we also were able to take a look at qualitatively, being that they're directly proportional. With this, we can state that all of our qualitative trends from before were verified using our quantitative model. So now for the last step of the presentation, let's take a look at some limits discussion. So, the task once again states, how is the maximum height of the fountain? And here it's important to ask ourselves, is the second jet actually always smaller than the first? To find this, we can just try to minimize the first jet. Take a look at our plot from before. We can do so by minimizing the ring velocity. This also minimizes the first jet. Furthermore, we can take a look at the relationship of the height of the second jet against its mass and see that there's an upwards increase. With this, we can state that as we increase the mass of the ring and also decrease the drop height, we can obtain a greater second jet. So before ending of this presentation, we can take a look at such an example. And here we can see that with a very great mass, the first jet reached about this height, while the second jet reaches way beyond that. So, in conclusion, we have shown a reproducible release mechanism, then investigated qualitatively what's actually happening here, from the free fall of the ring to the first jet being induced, to the cavity collapse, and to the second jet being induced. Went on to model our problem using some energy relationships, and then modeling it using a potential field. Then ended up with some parameter comparisons. And at the end, also discussed the limits of when the second jet is actually greater than the first. With this, I would like to thank you, and I'm now looking forward to a discussion with the opponent.
Okay, so thank you for your presentation. So firstly, do you think that the water tank size actually affects the height of the jet?
Well, if it's way too small, yes, but I don't think it is
Okay, so it's not really observable in your experiment. So then, can you explain to me how it's found out experimentally as well? Like how
it's found out experimentally. We model our problem as a mixed boundary problem, defining certain conditions,
so can you use
and then solve the plastic brainstorm.
So you use numerical simulations to find it, or?
It's not a numerical simulation, it's a mixed boundary problem. So what you do is you define certain boundaries on a free surface. So below the ring, we have a boundary condition. On a free surface, we have a boundary condition.
But when
they find solve the plastic equation for these boundary conditions.
Also, you use the Bessel function. You solve the Bessel function.
Sorry?
So you solve the Bessel function to find the 4%, right?
So we solve it on a grid, stationary.
Okay. And then moving on, you said that the mass will affect the second ring, second jet height. But then does the mass affect the first jet height?
We can observe that approximately it does not. Only for
okay. Thank you. And then for experiment, how do you synchronize the two pneumatic packs? How do you synchronize them?
We use an Arduino controller, I think.
Okay. And then how do you track the height of the droplet?
Oh yeah, we use OpenCV. I'm sorry, maybe I skipped over that earlier. We use droplet tracking. I can show you.
So how small can the droplet be for OpenCV to detect it?
About 0.5 millimeters.
Okay. And then for the analysis, can you give me a qualitative explanation on why there's a larger mass will increase the Worthington jet?
Yes, because a greater mass actually opens up a greater cavity, which then increases the cavity they can collapse.
And how do you
calculate the second jet?
How do you calculate the second jet height?
I did not.
Then what is the graph?
Oh, sorry, it was a line of sight just to follow.
Okay, thank you. Okay, so today Team Hong Kong would like to host problem 3 ring fountain. So let's look at the problem statement. I'll read this. And then so from this problem statement, we can actually conclude 3 tasks. Firstly, to qualitatively explain the formation of the jet. We believe that is somewhat done. We would like to explain later on how it could be better done. And then secondly is the parameter analysis and the optimization. We believe that the parameter analysis was very good. They clearly explained some of the trends. However, we did not really see some kind of numerical analysis or any optimization of the problem. And then thirdly is a theory experimental agreement on the jet height. We believe that it was quite well done as well. I wanted to put a tick at, it's kind of in the middle of these two. So we believe that the task completion is partly completed. And then let me move on to the report summary. So firstly, they tell us about the formation of the first jet due to the convergence of the water at the impact. They gave us a top view on how there's like the inner flux of water, it will converge in the middle, and therefore there will be an upward flow of the jet. And then it also talked about the formation of the second jet, which is the cylinder shape and might be irregular. And then for the theory, they explained how there will be the corona and also the high-speed jets, and there will be so like the first jet will kind of break up, and also there's the presence of corona in here. And then for the experiment, they use it's a very good experimental setup. So they use a checkboard calibration and auto tracking. They use the OpenCV for the tracking of the height of the droplets, and then they also minimize the tilt of the ring during the falling while there are around 1 to 2 degrees tilted. We believe that it might be it should be fine as well. And for analysis, they plotted the percentage of dark pixels versus the height versus time. We believe that is quite a good way of approaching this problem because well, it can basically track the overall shape of the water, and also how there's a rise of corona. We believe that is a very good way of doing that. And then they also use the videos, they sync it to the velocity of the magnets of the dropping ring. We believe that is also a very good way to prove that it's proportional. We believe that is quite well done. So for the strings, let me elaborate on the strings. There's a lot in this presentation, of course. And then he considered like possible physical issues, and also he considered some of the limitations of the theory. We believe that's quite well done. However, some of the points we improved is that we believe that there's a ring, still a principle of ring field. We believe that it would be better if they use an electromagnet, which can therefore allow for it allows for a magnetized ring to drop down. And we're not really sure how many trials there were, so we'll ask them for that. And then the error bars were quite large as well. We understand it's a hydrodynamics problem. We believe that there were much more repeated trials would definitely minimize the SD. And then they mentioned about the copper rule, but they never discussed later on what does the material actually, does it affect the ring fountain? And then the bubble formation was also not explained by the theoretical model. So here is an overview of the discussion before I invite to the stage. So we'll be discussing how exactly the jet height will be found, because this is obviously the most important dependent variable in this problem, right? And then for the theory, we'll be discussing about the boundary conditions, and secondly about the radial control instability and also the surface tension in the jet. And then finally, I'll be moving on to the parameter analysis. With this, I welcome I invite the team very to the stage to discuss with me. So firstly, I want to see how exactly you actually track the jet the jet line because I'm not really sure.
So earlier, so for this, we have two setups, like I explained before. One for low release heights. In that case, the jet velocity, isn't that high, so you can track it using automated
Okay.
But in the second case, for our second setup, the jet velocity was so great, like reaching up to 12 meters per second, that we had to do it by hand.
Oh, so you use tracker to do it by hand?
No, I wrote a custom office.
So it's a Python script. Okay. Or a script.
Do you see any problems?
No. I was just trying to know what tracker we use. Because as you can see. As you can see, maybe OpenCV will detect some of the like stray text. So I believe here I believe as a user that this is definitely a good way to go with it. Also, because there are there's a presence of stray droplets that come out, right? So so do you think that measuring the tip of the broken jet would be better?
I don't, because then you would just go into taking a look at radial plateau and looking at how small perturbations and the surface tensions create these colored droplets. And I think that's not the whole point of the task. The point of the task is to investigate how the maximum height of the jet, not actually take a look at radial plateau and so on.
Oh, okay, but I really want to explain more about the radial plateau instability. So because I see that can you switch to the equation with the maximum height, like predicted from your equations. So as you can see here, I believe it's very important to find the radial plateau instability. So right here, I can see that there's a presence of radial plateau. It will break up to small jets, like small water droplets. Have you modeled that in your qualitative explanation?
But once again, I don't think it's the point of the task, because the task asks for the maximum height, and I think it's more about the phenomenon. So how was the first jet created, how was the second jet created? And I think there are two possible definitions, one being the highest droplet, and one being what you're mentioning. So I do agree, right, that this could be interesting. It's not the main point.
But then, can you move on to the equation with basically the maximum height, right? Because I'm not really sure. So because you need to model this type of phenomenon, so I would actually suggest you to find out the boundary radius for the radial plateau instability. So then it will split up to some kind of droplets, right?
So I think there's a problem with this, because you would actually have to find the radius of your jet. And for this you would need this full CFD, because you can't actually approximate it to be a perfect cylinder, for example.
Yes.
Which is simply be incorrect. And to actually find, for example, the radius up here, which you would need to know for your surface tension and then your radial plateau, you would need a full CFD anyway, so then I could just model my whole problem using a full CFD. So I don't really
I agree with the reporter on this. While it might be while CFD may be have you done it? Have you tried using any simulation?
Yes, I have.
I assume it's Basilisk, right, from the interface. So the CFD,
I haven't shown it in my presentation because we didn't use it because it ended up being computationally very, very expensive. However, we did deploy a Navier-Stokes model at some point, somewhere maybe.
And actually, I believe there are some kind of models that can actually find out the radius of jet. While for the first jet, you can see that it's actually a very thin jet. I'm not talking about the second one. So for the second one, it might be very hard to find out because it's basically the angle here is very long, right? But then for the first jet, this angle is actually very, very small. So I believe that in some way you can actually approximate this in order to find out the jet rate, and then you also model the air drag on the boundaries of the.
I think that's very interesting for saying that for maybe small in a radius, you could maybe approximate this to be a cylinder. So it would maybe be a thought that you could try out. So, but once again, I don't quite think that radial plateau is the whole point of this task. Although I do think it's a very interesting proposition you make.
Yeah. Okay. And then moving on, we believe that the radial plateau has already used up some of the time already. So secondly, I want to discuss about how do you actually estimate the dropping velocity, the ring velocity? So do you just use how do you track the metal ring going down?
So we just extracted it from our experimental.
So you used OpenCV again,
yes,
too.
Because for the same thing we use for our jet velocity.
Okay. I meant the metal ring.
Exactly.
Yeah.
But with the same program, we then before track the ring going down, and then from that we could.
Yeah. Okay. Because originally I thought you were just using V equals to GH.
No.
Yeah. Okay. I understand that. And then you said about I asked a question about do you think the water tank size actually affects the ion index? Well, we would like to discuss more on that. What do you think about the tank size? Yeah.
I think for the first jet it has almost no effect because if you think about it, it's pretty much created
But then the problem is that if you actually approximate, like the tank size could be the same as so the tank size would be actually the same.
I just want to make one thing clear. And from my extensive videos, we were able to see that the first jet was created in less than 1 millisecond.
Yeah.
And due to this, there can't be any water effects because it's almost created instantaneously due to what we compressible, and then just all of the kinetic energy being given into the energy. For the second jet, we could maybe argue about it. However, I once again don't think that with our tank size it would have an actual relevant effect.
No, my issue is that if you approximate the R out with the tank size, then that means that's it. And then there's the R in there as well. So this means that the pressure here will be much larger because all of the water must be forced to go through this hole. So basically, all the jet height will be much larger than that. So I'm not really sure if you have captured this in your plot.
So I don't really have to because the sector lambda. There's no way.
So do you think that the lambda changes as the tank size?
I don't know because for column wheel it's like Q so just the water pushed away by the wind in a certain time step divided by the water flowing into the jet. And while I do agree that the water flowing outwards would increase with a greater tank,
exactly.
we only consider the water flowing inwards here, and we can find it. And all of the water flowing inwards is actually within our boundaries, so we actually very easily find out that it does not affect.
Okay, and then have you found out have you found out how the metal ring decelerates after it reaches the water, or do you think that's not important for the first jet?
So for this first jet, it's not relevant because, like I mentioned before, we assume the ring to have a constant velocity at the time of impact.
Okay.
Considering a small enough time step when it's not decelerated yet by the water.
Okay, I believe that approximation can be done. However, I would suggest the reporter to actually calculate the atom mass from the water that is going to be pushed down, and that is more important because that is important when you also model the second jet. We believe that it's kind of missing in the analysis, but the second jet, one way of approximating the second jet from the first jet is that you have the atom mass, and then you actually calculate the radial flow of the water in the middle, and you apply the geometric focusing factor, and then you can find the second jet height. So we believe that would be a lot better, because you can actually model the dropping velocity of the ring.
Well, I agree. Just to make it clear again, I don't think the mass has any effect for the first jet because the deceleration has any effect on the first jet.
But because for that reason,
I think this could also be just experimentally error, so it's almost perfectly straight. And you can it's less than 0.5 increase by increasing the mass by 3 times.
Okay, so so is this different materials of the ring, or how
this is once again a line of sight. I answered this in your.
No. I was asking if you change the mass, you change the R inner and R out.
Oh, I saw it in the presentation. I just want to make one thing clear.
Okay.
So our ring was actually made up of 3 distinct parts. One being a 3D printed outer part, then one being a 3D printed inner part, and then we had a copper ring in the middle. The copper ring was to ensure that we still had metal properties, while the outer and inner part, they were 3D printed, so we can easily variate the outer and inner diameter.
Well, then do you think, is this a metal ring anymore? Do you think the material actually affects the jet height? Because personally, I think
it depends on if you're talking about the first jet or the second jet.
What about the first jet and the second jet?
So of course, if I were to make just a paper ring, of course it wouldn't create the same jet velocity to make a metal ring. However, if we stay with reasonable densities and reasonable masses, I think it's approximately the same. And I do think that it's a metal ring, as I calculate the average density for you, and it would still be around.
Thank you. I think we just get the 5 seconds.
Okay. So you would volunteer your limit.
So firstly, we clarified a lot about the jet height because because personally I believe that the radius plateau instability must actually be modeled in this case because it actually measures how the radius of the jet, how it gets too thin, and that means the water will be divided into a few of the droplets, and therefore it might significantly increase the height because the momentum from water jet actually focuses onto the small water droplets. So we definitely believe that this should be modeled some way inside the simulation and moving in the simulation or experiment in general. And secondly, we also asked about how the tank size actually affects. We believe that it does. The report thinks it doesn't really have an effect. And finally, we actually found out how it's not actually calculated, and also how there's actually 3 parts in the ring. So I believe that it's very the whole opposing definitely clears up some of the misunderstandings inside the presentation. So thank you.
So we now go on to questions from the review.
First of all, I want to thank you for such an amazing discussion between the two of you. My first question would be to the reporter. Can you define what you mean by a fountain?
So I define it as the highest droplet generated by the flood waters.
Opposition, do you agree with that definition?
I agree that I think that both should be actually tracked, but I believe the first.
Sorry, thank you. What is the difference between a fountain and a jet to the reporter?
I don't think there's a lot of difference actually.
Okay. How was your maximum height measured? Was it the highest droplet?
Yes.
Okay. What is the significance of the ring shape?
Do you mean, well, a ring is defined as...
As in, if you have a flat disc with no hole in the middle, as opposed to the ring shape, what do you think is significant?
I don't think it's defined as a ring, but in that case I would have no first jet, but I would have a second jet, which once again, because the cavity collapsed in a single point, creating an anomaly.
To the opposition, you mentioned bubble formation in your speech. What is the significance of bubble formation?
Bubble formation.
Bubble formation.
So I believe that the bubble formation refers to the formation of the cavity as well as the ejector sheet. We believe that the energy dissipated, while there's a conservation of momentum during the collision, we believe the energy loss can be due to that.
Okay, I have another question. Do you think it is correct for the reporter's model to neglect drag?
I don't believe that. So that's what I've said in this as well when we were talking about the radiator plateau instability, that air drag should also be considered. Yeah.
Reporter, why did you neglect drag in your model?
I did not. I was just stating that it was a simple ballistic flow with air drag. Maybe, sorry, I forgot to say that.
Okay. Opposition, in your discussion you brought up the significance of investigating the jet's radius. Why do you think that?
Well, because the jet radius basically makes the radiator plateau instability to happen.
For the reporter, how did you control them? Have you considered mass of the ring when you changed the radius of your ring?
Yes, I kept the mass constant, and that was why I used an inner copper ring.
How would the copper ring fit into all of that?
Because then I can keep the mass constant.
Because you have 2 different materials for your ring.
So?
Because you have 2 different materials of your ring, how did you ensure the mass is the same?
Well, I can still calculate the whole mass of the whole ring, so when it's assembled with all of the parts.
Okay, what would you think changing the material of the ring would have any effect on the maximum jet height?
Well, it depends, I guess, once on the first or the second jet. For the first one, it must make almost no effect, no difference. But for the second jet, if it was...
Yeah, sorry about that. Onto slide 45. Why do error bars decrease?
Sorry?
Slide 45. That's okay.
45 arms.
That's it. Preparation time for
Good afternoon, everyone. I'm Tiffany from Team Australia, and today I'll be reviewing problem 3, ring fountain. First of all, we have some task expectations. We expected the qualitative explanation of the basic phenomena, including visual demonstration. We wanted well-documented and justified experimental setup, a controlled release mechanism, and we wanted investigations about relevant parameters. So onto the report. We have some strengths. So the reporter developed a new mechanism control for the tilting of the ring. They had a clear demonstration of experimental setup. They were able to compare results with the physical phenomenon. They had a clear outline of parameters. They were able to link model to physical stages of the phenomenon, and they had great time management. However, areas for improvement: firstly, they didn't give a clear definition for a fountain in their presentation. They didn't explain formation of the ring's cavity. They didn't explain characteristics of the whirling jet and how this was different, for example, from the annular jet. They had limited qualitative explanation on the phenomenon, which could have been more prioritized and spent more time on. And with the addition of the copper ring, mass was not controlled for the radius parameter, and that limited explanation on how tilt angle actually impacts jet height, which they had a setup to account for, but they didn't explain the significance of it. That lack of qualitative physics explanation regarding change for each parameter, and their experimental scope was relatively small. Onto the opponent, they have strengths. They pointed out a lack of qualitative explanation regarding each change in parameter. They pointed out the ring tilt observed in multiple experimental videos, which I also noticed. They pointed out a lack of trials and a small experimental scope. They pointed out large error bars and lack of error analysis, and they pointed out missing parts of the phenomenon, for example, the bubble formation. Some areas of improvement for the opponent would be they have poor time management and prioritization in their discussion. They raised topics of minor importance and spent a lot of time talking about these. And while some improvements and suggestions were given, most problems were left undiscussed, and they did not follow up on some clarifying questions which I would like to see. On to the discussion analysis. So first of all, the first point raised by opponent was droplets were not accounted by the model for maximum height of the jet. The reporter's response was, this could have been interesting to investigate, but it's not of top priority in this phenomenon. We agree with the reporter, given it is quite difficult to model the maximum droplet height. This was reasonable. However, this question was not of great priority. The next one would be, the next topic raised was there are some models that can find out the radius of the jet. The reporter's response was they investigated briefly with some equation. However, they could not find anything conclusive. We agree. We actually disagree with both in this situation. We believe that the priority of this task is the maximum height, and the focus should be optimizing it rather than focusing on the radius of the jet. The third point is how is the ring velocity tracked, and the reporter's response was that OpenCV tracking was used again. In this case, we agree with both. This is an important question that gives more insight into the experimental method, because it's a part of the experimental setup, and it's important for us to understand what the reporter actually did. Our next point of the discussion would be about how the water tank dimensions might affect the maximum height. The reporter's response was that dimensions were rather negligible with limited effects. In this case, we agree with the opponent as the water tank dimensions greatly affected the boundary conditions of the interactions between the ring and the water. Additionally, the distance the ring falls into water would also change. And lastly, onto the missed points. First of all, they didn't discuss the significance of the ring shape, and that was brought up in my clarifying questions. I think there is the shape of the ring would have a big impact on the formation of the jet and the maximum height of the jet, which they did not talk about. The opponent also didn't really discuss with the presenter about how mass is controlled throughout the radius experiment, given that there was copper rings. There was 2 different materials. The qualitative explanation of jet characteristics was not clarified, including the different characteristics of the Rosington jet and the annular jet, and there was a lack of accounting for drag and mass changes in the radius experiment, and the opponent did not say why it was important, although they brought it up. Thank you.
Okay, so first of all, thank you for this wonderful opposition as well as the rear view. And first, I would like to answer your last question. Why do the error bars get bigger? It's because you can see here it's about up to 12 meters per second, which is very hard to track. And for this, we have an increase in error bars. But every experiment was conducted over at least about 5 rounds, so to ensure that it was reproducible, and you can see that it gets better and better over time. Second, for talking about radio plateau, it's all about the definition, and I think it's totally fine to define it as the highest droplet for the fountain. And as for the tank size, which was mentioned by both the opposition as well as the reviewer, I do think it's completely fine for the first jet due to there not being wall effects at the time. But if you really wanted to, you could also define a boundary on where setting the potential to 0 on all of the tank sizes to model it. As for the mass, I misspoke earlier. The mass was kept constant by varying the infill of the pre-utility parts to ensure that mass was always constant. And furthermore, it was pointed out by the review as well as the opposition that there was tilt in the wings of the videos. However, all of these videos were actually from a qualitative setup where it showed that we did have tilt, and the experiments were conducted using the secondary setup, which had no tilt due to the improved dropping mechanism. I mean, you can see here that in the qualitative setup, there was in fact tilt. However, this was not used for the experiments. It was at least for the quantitative ones. And lastly, I just want to say, because it was talked about by both the reviewer and the product again, I did model the highest droplet and included air brake as well as ballistic throw. And yeah, that's everything for me. I think it was very productive, so thank you.
Okay, I can invite the 3 of these to announce the and
Question to the reporter. So for your measurements, the height you measure is the highest droplet.
Yes.
But your theory gives the velocity for the jet.
It gives the velocity right at the start when it.
So for the jet,
Yes.
the droplets and the jet are not the same thing as you said. So how can they fix for each other so well?
So if you, but you can, the relationship between the velocity of the jet and the height of the highest droplet, the simple ballistic one with some air drag, which is working on the literature.
So to the reporter, I would give you the task to form a 1 meter high jet. How would the wing have to look like?
So we were able to see that as we increase the impact velocity of the wing, it was directly proportional to the jet velocity. So that would be one point, and also decreasing the inner radius and increasing the outer radius also maximizes it. Because with a smaller inner radius, there's like a geometric effect of forcing the kinetic energy transfer from wind to the water for a smaller hole.
So higher drop height than the large
Radius with a very small hole in it.
One last question. All your error bars are actually theoretical error bars, or is it just standard deviation of
It's a standard deviation of experiments.
You mentioned
Well, I believe that it's an interesting phenomenon because when you actually minimize the water tank size, it may actually be creating it may force more water to actually go through the hole, therefore increasing the lambda. And when it approaches, then the lambda will go from 4% to equals to 1. So I believe that it will be an interesting phenomenon and how it can actually optimize as well.
In your theory, the mass and the velocity of the ring only occurs inside the energy or another way as well?
No, so we assume that the velocity is constant.
Yeah, but like in your equations, for instance, do these parameters only appear inside energy together?
Yes.
But then later, when you change mass and velocity differently, why do you get different results eventually? So
Once again, so it's not actually a theoretical line, which are shown later for the mass. It's just a line of sight. I should have labeled it better. So these are just.
okay, but so your theory doesn't account for this kind of.
It does not account for mass because I think you can see here that it's neglectable for.
And do you can give a very short explanation the why this happens?
Sorry, why the
So can you give just a very quick explanation of why this happens in this case?
Yes, because I believe so. We assume that the first jet is induced in a very, very, very small time step after the impact. And for this reason, the mass does not play any role because it's actually not decelerated by the water, and the deceleration by the water does not actually affect the first being created. So we just have the energy being